So our second total energy question is a cooling curve question, a little different from the first example we did. So this question reads, calculate the total energy change if 2.5 grams of steam at 120 degrees Celsius is completely converted to ice at 0 degrees Celsius. So as we mentioned with yesterday's example, we know it's a total energy question because we're going from steam to ice. So we have our phase change, also going from 120 to 0, so there's our temperature change. So with that, we need a curve. As we spoke with yesterday, with our curve, what we should put in is our initial temperature, our final temperature, and any critical points that fall within the middle of that range. So our initial temperature here is 120 degrees. So we're going to put that in the top. Final temperature is 0 degrees. And then the critical point that falls within that range between 0 and 120 is 100. This one can be a little bit tricky because our final temperature here itself is a critical point. Or 0 degrees, which you know is the freezing point of water, or the melting point of ice. So we'll talk about that when we get to our curve, but there's just this different situation we should be aware of. So in this case, when we're drawing our lines, we're going to start up top in this case, so with our 120. So notice for our cooling curve, we're going to move in the direction down and to the right. So first thing that should happen is that our temperature is going to decrease because we are not yet at a critical point. So our temperature will go from 120 down to 100. We're changing as the system loses energy, that our temperature is going to drop. In this case, we're going to drop until we get to 100 degrees. Because at 100 degrees, we know what will happen is it's going to convert from a gas to a liquid. And again, during a phase change, our temperature will remain the same, and that's why we're including our horizontal line. So after our horizontal line is done, so we're saying it's completely converted to a liquid, we're saying our system is going to cool, meaning our temperature is going to drop. And in this case, it's going to drop down to 0 degrees because that's our next critical point. Now, with the reading of this question, this says that it's completely converted to ice. So what we've shown here is that we have cooled our liquid. At this point, we strictly have a liquid, so we have to show the last horizontal line right here because we need to show it converting from a liquid to a solid. So you need to be careful when you do total energy questions that either start or end at a critical point because there may or may not be a horizontal line at that point. Really important to go through the wording of your question. So, as we talked about in the other example, what we should do is we should label each section in terms of what type of energy we have and what state of matter is. So between 120 and 100, we know that that's a gas. So I'm going to put a G there, and we convert here from a gas to a liquid. Between 100 and 0, we have a liquid, and at 0 degrees, it goes from a liquid to a solid. So there are our states of matter. With that, I'm going to put on our types of energy. Again, diagonal lines are during temperature changes. Temperature changes are described with a heat calculation. So we'll put a lowercase q, and again, I'll put the subscript in. Here we have a delta H because our temperature stays the same during a phase change. And from gas to liquid, that is condensation. So I'm going to put my COND subscript. Here we are cooling from 100 degrees down to 0. That's going to be another heat calculation, so Q of our liquid. And then the last one, again, temperature stays the same. So we will use delta H, solidification. So now that we have our curve and we have 4 sections on our curve, what we can do is we can go ahead and write our total energy equation that we're going to use at the end. So and again, all we're doing in every total energy question is we're going to make a sum of all of our different points on our curve. So we have 4 points here. So we will write that our delta ET, in this case, is going to be the sum of all 4 points. So Q of our gas plus delta H condensation plus the heat for our liquid plus delta H solidification. So once we've done and calculated all 4 of those variables, what we can do is we can come back, add them together, and then we should come up with a final answer. So next point is to go ahead and calculate each 4 of those separately. So our first one is going to be heating our gas. I use the word heating just because we represent that with the letter Q. In this case, reality, it's cooling. So we're going to use Q equals. And again, with heat questions, we always want to make sure we're using MC or VC delta T. Here we're using MC delta T because the amount of substance is measured as 2.5 grams, which is a mass measurement. So heating our gas is 2.5 grams. Our C value is for water vapor. So for water vapor, that's 2.01. joules per gram degree Celsius. And our temperature change decreases by 20 degrees. And this is the catch with cooling curve questions. Cooling curve questions, we really have to be careful with their state of matter. They should always end as a negative answer. And again, for heat calculations, that's because we have a negative delta T. So our temperature is decreasing. It's 100 subtract 120, and that's where the negative 20 comes from. So with that, I report that as an answer. And again, we're not worried about significant figures. It's just a rounded answer. So here we will get an answer of negative 100.5 joules. So there's our answer for the first part of our curve. So our next part is going to be our delta H condensation. Delta H is equal to N times H. And again, with the proper subscripts in there. So when we do this, again, our N value is going to be our mass divided by our molar mass. So that'll be 18.02 grams per mole. And that comes from H2O, 2 hydrogens, 1 oxygen. So mass divided by molar mass. Our molar enthalpy of condensation, again, it's an exothermic phase change. So we're going to use our negative 40.8 kilojoules per mole. So we make sure we have that negative in there. And again, with any cooling curve question, it's a negative delta T for any heat calculation, and it's a negative molar enthalpy when we do our enthalpy change. So that will give us an answer for this part to be negative 5.660 kilojoules. So there's two parts done, negative 5.66, which brings us on to our next part. So our second heat calculation is for Q of our liquid. Same equation as above, still MC delta T. Our mass is 2.5 grams. Different C value here because it's a different state of matter, 4.19 joules per gram degree Celsius. Our temperature change here is going from 100 down to 0. So it's a decrease, make sure we include the negative, of 100 degrees Celsius. So Q over liquid, that will work out to be negative 1,047.5 joules. So there's step 3. And on the last step is delta H solidification. And we need to include this because we are converting from a liquid to a solid. So N value is our mass divided by our molar mass. So 2.5 grams divided by 18.02. And our H value is going to be negative because it's an exothermic phase change. It'll be the opposite of fusion. It's negative 6.03 kilojoules per mole. So it gives an answer for that step of negative 0.837 kilojoules. So we have our 4 answers. Now that we have our 4 answers, we can go ahead and add those together, and we can add them together back in our original equation. So what we also have to remember is that when we're adding these 4 answers together, they have to be the same units. So we have to convert them all to kilojoules or convert them all to joules. I'm going to convert these two values, two joule values or heat values, into kilojoules. So when I scroll up and plug our numbers in, so negative 100.5 will be negative 0.1005 kilojoules. So joules to kilojoules divide by 1,000. Our molar enthalpy, or enthalpy change, of condensation is negative 5.660. Heat calculation for the liquid is 1.0475. And then our last value is negative 0.837. So when we go through this, one thing you always want to remember with a cooling curve question is all of your values should be negative. So yesterday in heating curve questions, we said every value is positive and our final answer is positive. But with cooling curve questions, every step should be negative, and then our final answer will be negative. So here we have 3 significant figures in our answer because we have 3 in this measurement. We have 4 in this measurement. We always take the value with the smallest number. 0.0 technically is no significant figure, so we don't use that as something to direct us with our reporting of our answer. So here with 3 significant figures, we should get a final answer of negative 7.65 kilojoules. And if you put this in joules, that works just as well. So just to recap a few things, with this we want to make sure just that we have the proper number of steps. So we should see 2 temperature changes, so from 120 to 100, and 100 to 0, and 2 phase changes, steam to liquid, and then liquid to solid. So we have to represent that on our curve, make sure that because it's a cooling curve, every step is negative, and then we add our numbers up. In this case, we get a negative 7.65.